Hello all. Today we are going to discuss lecture number 3, that is basic organic chemistry. The syllabus based on SKU Sidokanu Murmu University Dumka, semester 3. Okay, this is UG course, semester 3 UG course. So they have like within 15 days or 20 days, maybe they will have examination because form fill up is already over. So they are waiting for the examination. So before that, I thought let the syllabus completed and the notes also I should provide you, concept as well as notes also I am providing you. So please utilize this. So today we are starting basic organic chemistry lecture number 3. Previously we have completed classification and nomenclature. In detail we have completed. So do practice. Okay. Then today we are starting the hybridization. As I told you, the next class I will start with hybridization. So this is your hybridization. Okay. So hybridization and shape of molecule. So how this is related, because in this case, because this is going through in basic organic chemistry, so your hybridization will have only the limitation till sp3, sp2 and sp, correct? If you are going through this hybridization in your inorganic, that we call it VSEPR theory or valence bond theory, there you will find like entire molecule, whether it is your uh, organic, like this carbon molecule. Apart from this carbon molecule, there are many molecules like ammonia, like your phosphorus pentachloride, sulfur tetrafluoride, sulfur hexafluoride. So everything you have to determine over there, okay? But here in this, in your semester 3 UG, there is the limitation, only carbon elements hybridization you have to see, okay? The carbon compound making carbon atom is making compound, only those hybridization you have to see over here, correct? So what is hybridization? First of all, why hybridization is taking place? Okay, before writing, just we'll discuss a small why hybridization is taking place. What is the requirement for hybridization? See, there will be two condition, okay, or we can say that two basic concepts. uh, if it is uh, to fulfill those condition, okay, or to fulfill those concepts, this hybridization is taking place. See, in this hybridization, s orbital is mixing with your p orbital, correct? So why this s orbital is mixing with p and why p is allowing to mixing with s? Because see, s orbital, we know this is the size, okay, and this is the shape, okay, for s orbital. It means it is not having any direction. If suppose I am putting x direction, y direction and z direction, do we have any direction for this s orbital? If you are going this side or this side, all the three dimensionally, what happened? This s orbital is, or s orbital's shape is having uniform distribution, so we can't say the direction. So to get the direction, to get the direction, it is going to the p orbital and it is taking part in a hybridization, okay? So why s is taking place in hybrid, why s is going for hybridization? Because to get the direction, okay? And why p is already having direction, right? We have px, this is px, it means it is in x direction. We have py, it means it is in y direction. We have pz, it means it is in z direction. So here the direction is there, but still why it is going for hybridization? It is not like that it is going and helping s orbital. So there in chemistry there is nothing like the helping and uh, going away. It is like your some benefit this also should have, then only it will go and do hybridization, correct? So what is that benefit? See, p is having very less size. If we are talking about 2p, so this is the size, and suppose p orbital is making three bonds. Suppose nitrogen, I'm talking about nitrogen, it is having 2p3. Okay, so no need to go to nitrogen. If we are discussing for carbon, we can discuss for carbon also, because nitrogen again it will be more complexer, right? So for carbon it will be 2p2. So 2p2 means two electrons are there and which can make a bond, right? So this will be your 1p orbital. Let's suppose this is px, this is your another one, suppose this is py. Now suppose from with s orbital or again with p orbital, if it is making bond, so what will be the bond angle? it will be approximately 90 degree, correct? And if it is 90 degree, then see the distance that these two orbital will have repulsion. So this repulsion you will get. So to minimize this repulsion, what it will do, it will take place to the hybridization. It will take participate in hybridization, okay, with s orbital. So what it will get, its size will increase, and what will happen, the to make this minimize repulsion, it can be in a maximum distance apart, correct? So how it will be, it will be like this. After hybridization, the bond property will be looking like this. S will be very much small and this side will be p. So this is your, if it is one s and one p is mixing, so it will be your one, if it is one s and one p is mixing, you will get two sp hybrid orbitals. Okay, one and then one more. So two sp hybrid orbitals you are getting side, right? Now what will happen? Now it won't follow this axial property. Okay, it will be like, see, we know that in methane there nothing like no bond is in an axial. It is interaxial only, correct? Whether it will be in between xy or xz or yz, correct? So there, why P is going for hybridization? Why P is preferential for hybridization? Because it will get the like this repulsion. It is minimize this repulsion by increasing its size. Correct? Got it? And it will be like direction. It is required direction. That's why it is going to P for the hybridization purpose. Correct? So now enough concept I have given. Now you have to pause it and you have to listen again, so you will get to know why hybridization is taking place. This is like why hybridization is taking place. Okay, this is not why what is hybridization, this is why hybridization is taking place. Okay, if you are getting question like why hybridization is taking place, then this will be your answer, whatever I have discussed over here. But let's see what is hybridization. Okay, that we have to see. So before that, that hybridization is the mixing of S and P. We know that, and the redistribution of energy, and it should be in between the similar type of energy orbital. Correct. So we'll write it. Okay, because you require notes also. The mixing of the orbital having nearly the same, okay, energies. Okay, nearly the same energies means it is not like that only p orbital will participate. P and s, it is having very minimum energy difference. Okay, very minimum energy difference. So that's only the nearly the same energy difference. Or we can say that if it is 2s, then it will hybridization will takes place with 2p only. It won't be like 3s and 2p or 2s and 3p. It won't take hybridization. Okay, it should be in the same shell. So now, okay, with the same energies and the redistribution, okay, and the redistribution of their energies to form new orbitals having identical shapes and equivalent energies is known as hybridization, and the new orbitals are called hybrid orbitals. Are you getting? Okay. So it is similarly, as I told you, it is like the mixing of, okay, we are mixing of orbitals, okay, having nearly the same energies. Okay, nearly the same energies means one will be s and one will be p, but within the same shell. If you are taking 2s, then with 2p. If you are taking 3s, then it will hybridization will take place with 3p, correct? And the redistribution of their energy. Redistribution means whatever, like before mixing up, whatever the different, see, s is having different energy, p is having different energy, but after mixing up, it will redistribute. Means sp will have uniform energy in your in the entire hybrid orbitals, correct? So that is only redistribution. So redistribution of their energy to form a new orbitals having identical shapes and equivalent energy. That's what I'm telling. If all, like if 1s and 3p is mixing, then it will be 4 sp3 hybrid orbitals. Okay, like this, 4 orbitals will be there. So all the 4 orbitals will be identical shape and it will have the equivalent energies. Okay, is known as hybridization, and the new orbitals are called hybrid orbitals. So this orbital we call hybrid orbitals. Correct? Got it? So we'll just write it down next. The hybridization in Okay, the hybridization in the orbital of carbon can take place in three different ways. Got it? Three different ways. What all? This tetrahedral or sp3, then trigonal or sp2, or we can say diagonal or sp. Okay, these are all hybridization. Hybridization, correct? So first we'll start with sp3. Okay, first we'll start with sp3 hybridization, or we call it tetrahedral hybridization, correct? sp3 hybridization or tetrahedral hybridization, we say it. Okay, so in this tetrahedral hybridization, as I told you, if it is sp3, by seeing the hybridization model only, you can say how many s and how many p has participated and how many sp3 orbitals it has formed. So okay, uh, in a non-scientific way, I'm telling, see here 1s and 3p. So it will be 1s plus 3p. So how many it is? Like 4 sp3 orbitals. See, in a hybridization, always remember the it should be the like the number of atomic orbital is participating, that will be equal to the number of formation of uh, equal hybrid orbitals. If 4 number of atomic orbitals is participating, you will get 4 numbers of sp3 hybrid orbitals. If your 4 numbers of 3 numbers of atomic orbitals is participating, you will get the 3 number of hybrid orbitals. So here you see 1s and 3p. This 3 is not principal quantum number. So this 1 is your single s orbitals and 3p is your 3p orbitals it is participating. Okay, 3p orbitals. So this 3 and this 1 to total number is 4. So that's why we are getting 4 number of sp3 hybrid orbitals. Correct? So if it is sp2, so 1s and 2p is participating. So 3 sp2 hybrid orbitals will get. If it is 1s and 1p, then we'll get 2 sp hybrid orbitals, correct? So likewise we are getting. So first we will write up, we'll focus on the write up and then we'll discuss. Okay, so here we can write over here, okay, here all the 4 orbitals, okay, all the 4 orbitals, what all those 4 orbitals? 1s and 3p, correct? Are hybridized to produce 4 identical hybrid orbitals, correct? Known as, okay, known as sp3 orbitals with one unpaired electrons in these hybrid orbitals. Okay, repel one another. So what is that? See, in hybridized to produce four. See, four identical hybrid orbitals we are producing with 1s and 3p. So their total number of four atomic orbitals, and we are producing four identical hybrid orbitals, right? So known as sp3 orbitals with one unpaired electron. So each orbital will have one unpaired electrons. Okay, these hybrid orbitals, and it will be like electron is there. So each one each electron will repel to the other electron. Okay, so that repulsion will be there. So orbital repel one another. Correct? Get it? The four. Okay, the four hybrid orbitals should keep at a maximum distance from one another. See, it is obviously, if it is repelling each other, then what will happen? The repulsion, to minimize that repulsion, the four orbital, what it will do? It will just like due to repulsion, it will move far away, right? And then that moving far away is only the maximum distance from one another, right? So to how it will go to far away, it will maintain the distance with each other. So if we are maintaining distance from each other, so that we call a maximum distance from one another. Okay, now you have to write the angle, right? So what's supposed to be angle? It should not be 90 degree. So the angle between, okay, any two sp3 orbitals is tetrahedral, is tetrahedral. Okay, angle, we call it tetrahedral angle, and this angle is your 109.5 degree. Got it? 109.5 degree. So three dimensionally, if you see, it will look like a samosa, correct? So now we will just write it down. Carbon in ground state, GS is ground state. Okay, carbon in ground state, how it will look? 1s2. We don't require this 1s2, 2s2. We require this, and we have 1 and 2, 2p2. Okay, this is the ground state. Now what will happen? Suppose 4 hydrogen is approaching. I'll let 4 hydrogen is approaching. If 4 hydrogen is approaching, then it will go for it has to give places for 4 hydrogen, right? So it will be like taking participated all 1s and 3p. So total 4 hybrid orbitals it will make, and it will accommodate those 4 hydrogen. If suppose in case of sp2, only 3 hydrogen is approaching. So in that case, what will happen? It will just do with 1s and 2p, and it will form 3 hybrid orbitals, and it will accommodate those 3 hydrogen. Correct? So likewise, we have to see how many hydrogen is approaching. Okay, so based on that, we will create the our, like, we will do process the hybridization. Okay, now you see 4 hydrogen is approaching, but we have only 2 places. These two only can form a bond. This will not form a bond because this here, because we know that in a single orbital only maximum 2 electron can accommodate, and that is already filled over here, right? And this 1s2 will not participate because whatever bond is making and breaking, it will be only the valence shell, right? Outermost shell. So here the outermost shell for the carbon, it will be like n equal to 2. It means L shell. Got it? So here this will only participate for making and breaking the bond. So here you see, now it will just promote the electron. Before hybridization, it will just promote the electron. So promoting an electron, how it will promote? It will go from here to here, right? So in the next step, carbon at excited state. I'll just mark star mark, or I'll write here excited state. Okay, ES. So now 1s2 we don't read. Directly we'll go with the 2s, and then we'll go with the 2p. So one electron, another electron are just promoted over here. So this you just see. So now you got 4 orbitals where this 4 hydrogen can accommodate. So now what it will do? It will take place under hybridization. So hybridization is taking place over. Okay, hybridization is taking place. So after hybridization, all are 4 equivalent bond, 3 and 4. 1, 2, 3 and 4. Correct? So we can write these are the 4 equivalent sp3 hybrid orbitals. Got it? So this is your simple conceptual way. But in an orbital way, how it will form? So that also we have to write. See, 1, 2, 2s. So this 2s means not a number. This 2 is a principal quantum number. Okay. I'll just write this is an n, principal quantum number. Here the number of s orbital only 1. This is 2s is only 1, right? This is number of orbitals will be 1. But this 2 represents the principal quantum number, correct? Now this 2s is making hybridization with your p orbitals. It will be your pex. Okay. And then your py will be there. We are making sp3, right? Py. Then it will be pz. Got it? Now this will be in the process of hybridization. Now what it will form? It will form 4 identical. So before that, I used to do, you just draw a dotted line. So it will be easy to draw the hybrid orbitals with a equal distance, or else it will be difficult. So now we can just draw the hybrid orbitals. This is one orbital. This is another orbital. This is one more orbital. And this is backside. This is small one, you can see backside it is, right? So here the S lobe. Got it? So now you see. So here the bond angle, if you are seeing bond angle between these two, or band angle between these two, or bond angle between this one and the below one, or band angle between these two, or bond angle between these two, it will be always 109.5 degree. Okay, because this is tetrahedral bond angle, and these all 4, okay, these are all 4 identical hybrid orbital. Got it? These are all 4 identical hybrid orbitals. Now you can write it over here. What is that? Each of the 4 sp3 hybrid orbitals has 1/4 s and 3/4 p orbital character, correct? See, now 1s and see sp3, if I'm writing sp3, so total how many are there? 4. So out of this 4 part, s is having only 1. And what about p? P is out of 4. P is having this 3 part. So if you are adding this, it will be 4 by 4. It means 1. So you are getting 100%. So first 1 by 4 into 100, it will be 25%. So we can say that 25% as character. 3 by 4 into 100, it will be 75% P character. Correct? So these are the orbital character we are taking out. Okay. Orbital character and form 4 sigma bonds by pairing with electrons of other 4 atoms or groups at their axis. Correct? Pairing with electrons of other 4 atoms or groups at their axis. Got it? So suppose you are taking example for methane. This is how it is pairing. Sorry, how it is pairing up. See, this is the carbon's hybridization. This is the first. We'll draw the sp3. Okay. Okay. This is the back side. Now these are the hydrogen. Hydrogen, 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 hydrogen. So see 2 electron. So the next question, it is 109.5 degree. Next question can generate what is the bond nature between this? This is hydrogen, 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 hydrogen. This is your carbon. So what is the bond nature between hydrogen and carbon? So this we know that sigma bond, but they may ask what is the nature of this sigma bond? So it will be sp3 of carbon is overlapping with s orbital of hydrogen. So this bond nature is sp3 to s. This overlapping is taking place between sp3 to s, correct? So it is not like that always sigma bond will be sp3 and s. It can be sp3 and sp3 also if we are taking example of ethane. So in ethane, see hydrogen, 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 here carbon, here hydrogen, hydrogen and hydrogen. Now you see what is the bond nature of this bond? It will be sigma bond again, but the orbital overlapping, what is the orbital overlapping is taking place between these two carbon? This one. See, what is the orbital overlapping? It will be sp3 of this carbon and sp3 of this carbon. So that is going to change, but you have to see the question what they are asking. They are asking whether they are asking in between carbon-carbon bond or in between carbon-hydrogen bond, or what is the hybridization of this molecule. Based on that you have to say. See, it will be sigma bond. This also sigma bond. But here sp3, sp3, here sp3s, correct? So likewise you have to see. Got it? Next will be your sp2. Okay, sp2 hybridization. sp2 hybridization, that is your trigonal hybridization. Okay, trigonal hybridization. Got it? sp2 hybridization or trigonal hybridization. What is happening over here? Just write it down. The 2s, this 2 is principal quantum number. Okay, and 2 of 3 2p orbital. So what does it means? Why I am writing like this? If I am writing this number, it means principal quantum number. If I am writing like this, it means the number. Okay, correct? This number is principal quantum number. This number is principal quantum number, and wherever I am writing this TWO, THREE3, these are the number of orbitals. It means 3 2p orbitals means 3 number of 2p orbitals, 2 number of 2p orbitals. Okay, so what is happening? 2s and 2 of 3 2p orbitals. Okay, like 2px and 2py. See, hybridize to form 3. See, this number means 3 number, 3 identical hybrid orbitals. Okay, called sp2 orbitals. Got it? Called sp2 orbitals. And since the unpaired electron, as same thing, whatever you have written for sp3, similar way we will writing over here. So that's why we are putting since the unpaired, okay, since the unpaired electrons in 3 hybrid orbitals repel, okay, repel one another. The 3 hybrid orbitals should be so arranged, okay, that they keep at a maximum, okay, distance from one another. Got it? From one another. So now you see you have 3 orbitals and you are just want to keep a maximum distance from one another. So what will be the angle? It will be like 360 divided by 3. So 120 degree the angle will be. Just we are going to write over here. The angle between any two sp2 orbitals is 120 degree. Correct? We can write the third 2p orbitals, the leftover, okay, whichever which have not have participated in hybridization. So I'm talking about that orbital, the third 2p orbital remains unhybridized and perpendicular, okay, this is very much important, perpendicular to the plane of the three hybrid orbitals. This is sp2, correct? So, have you understood? See, the three hybrid orbitals are in a plane. In your, we can say that in your table, maybe the plane it is follow the blackboard, or you can say the plane of your page. It will follow like that. But the unhybridized orbital will be your above the plane and below the plane. That it will follow. Okay, so we will try to draw it. Before that, let me see the carbon. I'm not going to write the ground state directly. I will write the excited state. But in a first time, if in first time, like if suppose in examination directly they are asking what is sp2 hybridization, explain it. So that time you have to write the ground state, and then three hydrogen is approaching. So you have to make the like three orbitals is taking participated in hybridization, and then you have to complete it, right? So here direct excited state I'm writing. Okay, one, and one. Okay, it's already excited. So now we know that three hydrogen is approaching. Okay, if three hydrogen is approaching, what will happen? Only this three orbital will take place. So 1s and 2p. So now hybridization, correct? In hybridization, what will happen? These three will be together, and this, I'll just change the color. This is unhybridized. Okay, this one is unhybridized. So these three are hybridized. These three are hybridized. So we can say this is your sp2, this is also sp2, this is also sp2, and this one is unhybridized. It means this three will be a plane in a plane, and this will be in other plane. Correct? So how in orbital picture we will see it? See 1 2s is the principal quantum number, and let me take px and py and do the hybridization. How it will look like? See 1 2 3. So the bond angle is 120 degree. Got it? This is sp2 orientation orbitals. Okay, we can write three sp2 orbitals, 1 2 and 3. Three orbitals, and you know this is in a plane. This is in a plane. Okay, now to draw the unhybridized one, just change it to this way. Okay, so this is the carbon. This will three bond it will make with hydrogen or wherever whatever you want. This is hydrogen, hydrogen, and hydrogen. Now one is unhybridized form, right? So it will be in this form here and here. So in this only one electron will be present. So this is your unhybridized p orbital, and it will be 90 degree with this and with this. Okay, it will be 90 degree. Here also it will be with 90 degree. Okay, with all this it will be at 90 degree. I'm talking about this unhybridized orbital with this hybrid orbital sp2 sp2 sp2, but in between these are 120 degree, 120 degree, 120 degree. Got it? But between this hybridized unhybridized p orbital and this hybridized orbital, it will be always 90 degree. Okay, it means it will be the above the plane and below the plane. Okay, so if we are taking the ethylene molecule, okay, so I'll take the, okay, here also I can draw it. So how this molecule we can draw it? So see, this is sp2, this is sp2, and this is sp2. Three sp2 I have drawn for carbon. Here one hydrogen, hydrogen, and this side also. This is sp2, 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 hydrogen, hydrogen. This is the molecular structure for this ethene, correct? Now you see we have each carbon one unhybridized orbital, correct? These two are unhybridized orbital. Now what will happen? This electron will jump over here. This electron will jump over here. Again it will jump over here. This again it will go over here. So this jumping will take place. Here also this jumping will take place. Now you see it's forming like a cloud. So we can say that this carbon and this carbon, one is sigma bond, another one is pi bond. Now question is arising here. These are the electron. Okay, these are the electron. Just fill up to two electron. So now if question arises, what is the bond nature of this sigma bond? This will be your sp2, sp2. Correct. What is the bond nature of this sigma bond? Carbon and hydrogen. This sigma bond. It will be your sp2s. Got it? What is the nature of this pi bond? This is unhybridized p orbital and unhybridized p orbital. But both should be same. If you are taking pz over here, here it should be pz. Okay, otherwise if plane is changing, then this overlapping won't be takes place. If once you are taking pz and another one if you are taking py, then there will be 90-degree difference, and then those hybrid those overlapping will not take place. Okay, lateral overlapping will not take place. For lateral overlapping, they should be in a parallel form, right? So these are the parallel form because in the same direction, pz, pz. So this is the pi bond, and this will be like p and p overlapping. So like that, they may ask you that draw the molecular structure. One example of sp2. Okay, sp2 hybridizations example. Okay, molecular level drawing they may ask you, or structure they may ask you. Then you have to answer based on this. Okay, next is your, you can write each sp2 hybrid orbitals has 1/3 s character and 2/3 p orbital. Okay, 2/3 p orbital character. Correct. Got it. Because see here the s character is increasing. If you are multiplying with 100, it will be 33.6 or 33.33. Here it will be your 66.66. Correct. So the percentage s character is increasing. Okay, and next will be your the effective size of these sp2 hybrid orbitals is slightly smaller than that of sp3 hybrid orbitals. See, size will be smaller. Why it is slightly smaller? See here in sp3, 1s and 3p were there, right? Correct? 1s and 3p. So if 1s and 3p, obviously the size will be large. Okay, size will be increased. If it is 1s and 2p, your size will decrease, right? Again, if you are taking 1s and 1p, again size will decrease. Okay, so according to size, if you want to arrange, it will be like sp3 have the bigger size, then sp2, and then sp. Always it will follow like this, correct? So sp3, sp2, and sp. And one more thing, see, s size is less. And here s size, see, we know that this is the smaller size and this is the larger size p. Here this is smaller, larger, smaller, larger. Now what is happening? See, the contribution of smaller size is only 25% over here. The contribution of smaller size is 33, increasing. So if smaller size contribution is increasing, what will happen? Overall size will decrease. Here you see in sp 50%. Okay, here 50%. The smaller size s orbitals contribution is 50%. If smaller size contribution, as I told you, as the smaller size contribution is increasing, overall size of the hybrid orbitals it will decrease. Sorry, if it is increasing, then size will increase. If the smaller size contribution is increasing, then your size will be decrease, or we can say that it will be small. Correct? If the large, or another way we can say, if the larger size contribution is increasing in this way, so here the contribution is less, here the contribution is more, again here the contribution is maximum, here 50% contribution, here 66% contribution, here 75% contribution, and the large size is larger. So the larger size contribution is increasing, your size will also get increased. Okay, that's why sp3 is having larger size orbitals. I'm talking about hybrid orbitals. So it will be larger than this, than this. This will be the smaller one. So in the next class, I will start with sp hybridization as well as the bond properties. Okay, we have the bond, influence of hybridization in bond properties. Influence of hybridization in bond properties. Okay, this I will start in the next class. So this sp hybridization as well as these two I will try to finish in the next class. Okay, so likewise before your examination I will complete entire syllabus. Okay, so don't worry, you will get all your notes over here, you will get the concept over here, and if you are getting any kind of doubt you can ask me through the comment section or in direct to my WhatsApp number, correct? So thank you for watching.